Hello there, and welcome back. In this video, we're going to begin our lengthy discussion of probability mass functions, which really allow us to combine a bunch of probability problems into one nice, compact formula, which can allow us to readily get any answer for a variety of problems in a matter of seconds if we really want. So in order to sort of guide this discussion of probability mass functions, we need to first talk about what it means to be a random variable. So what exactly is a random variable? And I'm going to typically represent this or abbreviate this as just RV. So a random variable represents the potential outcome. So the potential outcome of a random or randomized experiment. So for example, let's assume you're a store owner, and on any particular random day, you could have anywhere from 0 to 5 million people. So before you open the store, that particular number of people typically is going to be a random variable, right? So in that case, a random variable for the number of people that could walk into the store. Random variables are typically classified into two broad categories. The first is going to be a discrete random variable, and the second category is going to be continuous random variables. So examples of discrete random variables would be such as flipping a coin. So flipping a coin. So let's assume that the random variable we want to define is going to be x. So we can say x is equal to 0 if we get a heads, and we can say that x is equal to 1 if we get a tails. Right? So if we flip a coin, either x is going to be 0 or x is going to be 1. Sometimes we refer to that as a Bernoulli random variable. It's either heads or tails, 0 or 1, true or false, yes or no, that type of binary type of expression. Now in terms of continuous, you have a bit of a different type of variable to work with here. So for example, this could be the amount of time you spend on your cell phone every single day. So that means the amount of time, let's assume x, is usually a number anywhere from 0 to 24 hours. So you could spend 10 hours, 10.5 hours, 10.12367 hours, and so on. So you pretty much get a continuous interval from 0 to 24 versus the discrete case where you only have a couple numbers, either finite or countably infinite. That is also possible too. Because for example, how many people can eat in a restaurant, you could have 0, 1, 2, up to some upper bound that represents the maximum number of people that you can fit in the store. But if you have not defined that maximum, then the upper bound is virtually infinite. So in theory, you could fit an infinite number of people in there if you could find out a way. So now that we have variables, now we need to talk about functions defined on these random variables. So functions defined on, so we have two different variables, discrete or continuous random variables are called, so we have two different names for each of them, or one different name for each of them. So a function defined on a discrete random variable is going to be referred to as a probability mass function, or PMF for short. And usually we will write the probability that capital X takes some little value x is equal to something. So that's going to generate the probability of a particular variable taking some particular value. And for continuous random variables, we refer to them as probability density functions, or PDFs for short. And we will represent probability density functions of a random variable capital X to be capital or little letter f sub capital X of value little x, right? And there is reasons why we use p for probability mass functions and f for probability density functions. When you plug in a value x into a probability mass function, you will get a probability. But if you plug a number into x into a probability density function, you will not get a probability. So you may ask, well, what exactly do you get? Well, we will spend time on probability density functions at a later time. But for now, our focus will be discrete random variables and PMFs defined on them. So let us just go with a little example to sort of illustrate what a probability mass function is, how we can construct one, and also we'll discuss what we can do with it later. So example, let x represent the sum of the outcomes of two six-sided dice. Okay, so what exactly am I talking about here? So we're going to roll two six-sided dice. All right, let's draw a 3D picture relatively decently. All right, so there's our dice, and they're all going to be labeled, 1, 2, 3, and so on. So let's assume that's 3, 4, 6, and 1. So I'm going to define, say, I don't know, A to be equal to the first, B to be equal to the second, and I'm going to find X to be equal to A plus B. Right, so A can be anything from 1 to 6, B can be anything from 1 to 6, and X is going to represent the sum. Right? So remember, we actually talked about the sample space for this type of experiment, right? So S consists of all the two-dimensional vectors, 1, 1, 1, 2, all the way down to, say, 1, 6, all the way down to 6, 6, right? So we found that the size of the sample space was going to be equal to 6 squared, which is 36. Okay, and we can find out the event spaces associated to a sum of 2, sum of 3, sum of 4, sum of 5, sum of 6. And I'm not going to go through that, but we're going to be using that information here. So the minimum value that x can take is going to be 2, right? That's going to be generated from 1, 1. So what is the probability that x takes that particular value of 2? So that's going to be equal to 1 divided by 36. So the next value is going to be equal to 3. So how can we get a sum of 3? So that's going to be equal to the events 1, 2, and 2, 1. That's going to give us 2 out of 36. So how can I get a sum of 4? So that's going to be 1, 3, 2, 2, and 3, 1. So there's going to be 3 events out of the 36 possible events that can give us that. And technically you could go through 5, 6, 7, 8, 9, 10, 11, all the way down to the maximum value of 12, which is generated from the event 6, 6. Right? So if we were to fill out all of these, you should see a pattern. That's going to be 4 out of 36, 5 out of 36, 6 out of 36, and then 5 out of 36, and then it's going to decrease. And I suggest you verify that each of these probabilities are indeed correct on your own. So since I have a table of values, I should be able to generate a graph of this. So this is going to be x, and this is going to be the probability of those particular x values. So x is going to range from 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? And I can graph these fractions, but I'm not going to label the horizontal axes. And then I get this type of nice symmetric function. Right? Oh, why is my maximum value hanging out at 6? It should be at 7. There we go. My little triangle house looked a little bit lopsided. I was like, that doesn't look about right. So this table represents my probability mass function. So that is my PMF for x. Now, of course, it's not a pretty little function because it's not continuous. Now, you could find the equation of the line that passes through each of these points technically, right? But that line doesn't really make any sense for all of the values in between the integers, right? Because it's impossible to roll a sum of 3.2 as long as your sides represent integers, right? But if this is the PMF for my random variable x, then I have an associated graph for my probability mass function x. So how do you interpret this? So from the probability mass function table, I can ask, what is the probability that you roll 2 dice and you get a sum of 4? Right, so little x is going to be equal to 4. Then from this particular table, you can find that that's going to be equal to 3 out of 36. I can also ask you, what is the probability that x is equal to 8? And then you can look at that and be like, okay, that's 5 out of 36. You can also say, what is the probability that my little value x is going to be bigger than, I don't know, 3? So that's the same as the probability that x is less than or equal to 3 subtracted from 1, right? So this is going to be 1 minus the probability that x is less than or equal to 3. So what's the probability that x is less than or equal to 3? So that means x must be 3 or 2. So that's going to be equal to, let's just write that out, x is equal to 3 or x is equal to 2. They are mutually exclusive events, so I can just add up those events together. It's going to be 2 out of 36 plus 1 out of 36, which is 1 out of 3 36, which is going to be equal to 33 out of 36. Also, one very important thing about this table, that the sum from x is equal to 2 to 12 of my probability mass function values, so px equals 2, x equals 3, x equals 4, x equals 5. So if we sum across this x column domain, if we sum out the output range values, then we should get 1, right? So remember, the sum of all the probabilities in my particular sample space should come out to 1, and each of these rows of this table definitely do partition my sample space. So this is the very first and important property of probability mass functions, and a couple baby examples on how to interpret them. One of the very first important observations that you should make is the following. And one perspective of probabilities on random variables is that x represents all of the possible values that a population could take, and also how many elements that that particular value may take, or how many values are in that population, because it represents all of the possible outcomes, and the probability mass function or density function somehow relates the probabilities to all of those particular values. So in a way, capital X represents all of the possible values of a set, and the probability represents all the relative frequencies of each of those elements in that set. And you could also think of them as class-based things, because for example, 1, 6 and 2, 5 both correspond to a sum of 7. Therefore, that could be the class of 7, right? So capital letter X, the random variable X, could represent a particular value or even a class. And the probability will represent the relative frequency of that value or class, right? So there's definitely lots of parallels to these things. So if that is the case, then we can come up with the following conclusion. That means any calculation on X will be a parameter, right? So the probability mass function of a random variable represents a parameter or a parametric distribution or a theoretical distribution of the values of the probability of x. Nonetheless, it is a parameter, not a statistic. Now, what do I mean by calculation on x? Well, a function defined on x is definitely some calculation. Are there any other metrics or things that we could define on this that would also be calculations on x? And the answer is, of course, yes. So let me first introduce to you one very important one, and we call this the expected value. Some people will also call this the mean, and some people will also call this the first moment of random variable x. So expected value, mean, first moment, all synonymous, at least as far as this conversation is concerned. But each of these terms represents a different perspective of the same exact number or calculation that we're going to be calculating. So how do you calculate the expected value or the mean of a random variable? And also, why do we call it the mean, right? So, arithmetic mean, geometric mean, which mean would it be if it were to be one of them? So the expected value of a random variable x, and some people will write this as mu x, so this will be synonymous to the arithmetic mean of, for example, a data set, is going to be defined to be equal to the sum across all values x in the domain of your function times x times px of x, right? So let's just briefly describe what I mean by here. Some people will refer to this as the support of your function. This just means that the probability of all of these values I'm summing over x has a probability that's greater than 0, right? So we're not going to be adding up any values whose probability is equal to 0, because if it has a probability of 0, when we multiply that x value by it, you're just going to get 0, so you're just wasting time in those calculations, right? So we're just summing up across all values that are associated to a value for the probability or the random variable that has a non-zero probability associated to it. Okay, so let's just illustrate how to use this formula for the expected value, and then let's see if we can try to interpret it. So let's use the same exact example as before. So you roll 2 die and you look at the sum. So the expected value is going to be equal to, so what are all the possible values of x? So it's going to be 1 times the probability of 1 plus 2 times the probability of 2 plus all the way down to the largest value, 12, times the probability of 12. So what is that going to be? So that's going to be equal to, so what's the probability that we get a sum of 1? Oh, we don't have a sum of 1, right? So that's a waste of time, right? That's just going to be 0, right? So 1's not in the support of our function, right? That's 0. What's the probability that we get a sum of 2? So that's going to be 1 out of 36. And then we have 3, that's going to be 2 out of 36. And you do this all for all of the values, all the way down to 12. So what's the probability that we get a 12? That's also going to be 1 out of 36. So what is that going to be? So notice that we have 36 in all the denominators. I can technically factor that out just to make your computations easy. And you should get 2 plus 6 plus 12 plus 20 plus 30 plus 42 plus 40 plus 36 plus 30 plus 22 plus 12. Now, where are all these numbers coming from? So that's 2 times 1 is 2, 3 times 2 is 6. I'm just multiplying the values of x times the numerator of each of those probability fractions. And you'll get all of that out. Now, does this sum come out to anything nice? The answer is yes. Actually, once you do all that calculations out, you should get an expected value of 7. Very beautiful little number, right? That's the mean of the random variable x. So if you remember from our little distribution, let's do an extrapolation of those points. That's actually what value this 7 is associated to. So this, by chance, question mark, is the center of the distribution. So technically, if you have a symmetric probability mass function, then the mean should be in the exact middle. So then you see some very interesting parallels to both statistics and probability theory, which is one of the reasons why we sort of combine the two in our discussions. So that is one parameter that we can calculate. That's a measure of position, of course. What about a measure of variation? So then comes the second moment. The second moment of a random variable x. Now the second moment is not commonly used by itself. It's usually used to calculate the standard deviation or the variance. But the second moment is usually used to calculate it. So for example, the second moment of x is defined to be equal to the sum across all values in the support of our random variable for our function, x squared times their corresponding probabilities. So that's the second moment. So how would you calculate this for our example? So that means the second moment of our sum of dice is going to be equal to, so the smallest value is 2 squared times its probability. The next value we could get is the 3 squared times its probability, all the way down to the last value that we could get, squared times its probability. And once you do all that out, you're going to get 987 divided by 18, or approximately equal to 54.83 repeating. So that's the second moment. So of course you can interpret the second moment as a measure of variation. The larger the second moment is, the more spread out the distribution of my random variable will be. Now, variance. the formula for variance is actually a little bit complicated, but let's look at it. So the variance is going to be calculated as follows. So the variance of x, some people will write it as sigma squared of x, is going to be defined as the sum across all values of my support of x minus the mean of x squared times my probability function. Now this formula should look extremely familiar because that is the frequency distribution representation for the sum of square differences. We're just missing the, oh yeah, we're missing the n minus 1. But notice that if we divide the n minus 1 or n, because we're in a parameter world, that turns into the relative frequency of my particular x value. So this is similar, practically equivalent, to the x minus mu x squared times the relative frequency of a particular value of x. Is the same exact thing. By chance? No, of course not. But because probability and relative frequency are practically parallel in terms of the narrative that we can tell, right? So these are exactly the same, sorta. So this formula is a little bit complicated though. So let's actually work through a nice little proof of a nicer way to represent this. So we know how to FOIL, right? So the variance of x is going to be equal to, I'm just going to write the sum just because that's not going to change. I'm going to FOIL that inside. We should already know how to do that. So x squared minus 2 mu x plus mu x the quantity squared times px of x. And then what I'm going to do is I'm going to distribute this into those three terms. We should know how to do that already. And then we're going to have x squared times pxx minus 2 mu x pxx, so pxx, plus mu x squared times pxx. Now that I have my three terms, I'm going to distribute my sum over those three terms. I usually do not prove a lot of things, at least in statistics, or require them, but this proof actually has a lot of important things that you should know, so it's useful. So once we distribute that sum, what will we get? So we have the sum of x squared px. Now 2 and mu x are just numbers, right? Mu is just a number, it's just a mean. So we can factor that out of the sum, so we're going to have 2 mu x times the sum of x pxx. And then again, mu x squared is just a number, I can factor it out. I'm just going to be left with pxx. Now take a moment and pause this video and take a step back and tell me what each of these things are equal to. So the first thing is, by definition, the second moment of the random variable x. The next one is just the definition of the expected value of x. And what is this last thing equal to? So the sum of all of the probabilities should be equal to 1 because p is a probability mass function for random variable x. So remember that ex and mu x are the same exact thing. So we can just rewrite this as ex squared, the second moment, minus 2 mu x squared plus mu x squared. Combining like terms just gives us ex squared minus mu x squared. So in conclusion, we get this beautiful little formula that is very important. It's going to be equal to the second moment of the random variable minus the mean squared. This is going to be the most preferred representation of how we're going to calculate the variance of a random variable. And of course, again, some people will write this as sigma x squared, same exact thing. So for our particular example, you can find that you should get about 105 divided by 18. Now, there's another measure of variation that is going to be more preferred, and that's going to be the standard deviation of random variable x, which you can just represent as sigma x, which by definition is the square root of the variance of x. And for our particular example, you can find that that's approximately equal to 2.4152, or 4152. Okay, so in terms of how do you represent this, so if the standard deviation, the variance over the second moment is really spread out, usually the graph of the distribution is really large. Now, in terms of applications, like real-world applications, we're definitely going to get into them a little bit later, but at least for now, you should be comfortable with the calculations of the mean, second moment, variance, and standard deviation of a discrete random variable. So to close this video out, let us just do a brief example of a baby application on how we can use these probability mass functions. Of course, you're not going to be flipping coins in the real world, you're going to be doing other more exciting things. But later, when we start building more special probability mass functions, you'll notice that even though a flipping coin problem is not really useful on its own, there are several and technically infinitely many real-world problems that can be modeled exactly the same, which is why flipping coins and rolling dice and picking marbles from a bag are pedagogical examples that are commonly used, right? But we'll get into all those things later. So we're going to be flipping a fair coin 2 times. When I say fair coin, that means the probability of getting a heads or a tails is 50%. And let x represent the number of times you get heads in your experiment. So what is the minimum value of the number of heads that you can get in your experiment? So you could well, technically we can list out all of the possible outcomes. So we can have heads heads, we can have heads tails, we can have tails heads, or we can have tails tails. So those are all of our possible outcomes in our sample space. So the minimum number of heads you can get would be 0. That would correspond to t. So the probability of getting 0 heads would be equal to 1 out of 4. And what about 1? So the probability of getting 1 heads would correspond to 2 out of 4. I'm not going to simplify that. And the probability of getting 2 heads would be 1 out of 4. That would correspond to the HH element. So these are all the possible values. Therefore, this corresponds to my probability mass function for this random variable x. If you really want to, you can sketch the graph of this distribution. So 1 out of 4, 2 out of 4, this is going to be my probability axis. This is going to be my x-axis. And then I have 0, so 0. Well, my dot shouldn't be there. It's my origin. So 0, 1, and 2. And then I have 0, 1, and 2. So I have another little triangular distribution, right? Symmetric about 1. So take a guess, what do you think the mean of this random variable x is going to be via the last example and also this comment that I briefly made? So let's just find out and verify whether you are correct or not. So the expected value of x, again, is going to be the sum of all of our x values times their corresponding probabilities. So that's going to be equal to 0 times its probability plus 1 times its probability plus 2 times its probability. So that's going to be equal to 1 times 2 fourths, so that's going to be 2 fourths. And then 2 times 1 fourth, that's going to be 2 fourths. 2 fourths plus 2 fourths is going to be 4 fourths, which is equal to 1, which is again the center of the distribution. Now let us try and see how we could calculate our second moment. So if you want to pause the video, definitely go ahead and give that a try. So again, the second moment of the random variable is going to be the sum of x squared times px. So it's going to be equal to 0 squared times 1 fourth plus 1 squared times 2 fourths plus 2 squared times 1 fourth, which is going to be 0, so that cancels. Nobody cares about that. So we have 1 times 2 fourths plus 4 times 1 fourth. So that's going to be equal to 2 fourths plus 4 fourths, which is going to be 6 fourths, which is 3 halves. So I have my mean, mu x. I have my second moment, 3 halves. From these two, I can calculate my variance very easily. So my variance, remember, is going to be my second moment minus the mean squared. So my second moment is 3 halves. My mean is 1 squared. So it's going to be equal to 3 halves minus 1, which is the same as 2 over 2. So I have 3 over 2 minus 2 over 2, which is going to be 1 over 2. So my variance is 1 half. Then, how would I find my standard deviation? So my standard deviation of x is going to be equal to the square root of my variance. So it's going to be equal to the square root of 1 half, which is going to be the square root of 1, all over the square root of 2, which is 1 over the square root of 2, If you want to rationalize, definitely go ahead, but that's the square root of 2 over 2. So that's the standard deviation of my random variable x. A very familiar number for you trigonometry people, but aside from that observation, maybe there's a connection to the unit circle, maybe there's not, we don't know. To discuss later, right? So those are just the basics of probability and mass functions, which are just functions that describe the probability for discrete random variables. In the upcoming videos, we will take a look at several real-life examples associated to special probability mass functions that occur in several places. I'll see you there. Take care.